In a universe filled with countless celestial travelers, few moments excite astronomers more than when a visitor arrives from beyond our solar system. In 2020, a faint, icy body named 3I Atlas streaked across our skies, an interstellar comet born in another star's nursery. Its trajectory told us it had wandered for millions of years through deep space before gravity pulled it into our neighborhood. When it appeared, telescopes worldwide turned to follow its pale green tail, hoping to glimpse secrets carried from another star system. But 3I Atlas didn't stay long. Within weeks of its discovery, the fragile body disintegrated, scattering cosmic dust across the void. What remained were spectra, light signatures captured by Earth's instruments, revealing a composition rich in carbon chains, water ice, and complex organics. To researchers, these fragments became a puzzle. Could the chemistry of 3I Atlas be recreated on Earth? Could we simulate what happens on a comet that formed around another sun? Across laboratories, scientists began to design controlled environments where interstellar conditions could be mimicked. Temperatures near absolute zero, pressures a billion times lower than Earth's atmosphere, and intense radiation similar to what flows through interstellar clouds. These chambers would become miniature analogues of space itself. Inside them, thin films of ice, dust, and organic molecules are exposed to ultraviolet light or energetic ions. The goal: to watch in slow motion how cosmic chemistry evolves and to see if something like 3I Atlas could emerge again in the safety of a laboratory. To understand why this effort matters, we must remember that comets are more than wandering snowballs. They are time capsules from the earliest stages of planetary formation. Each icy grain preserves molecules forged before our sun was even born. When such a comet from another sun passes through, it's like holding a relic from a completely different cosmic history. Recreating those reactions on Earth lets scientists trace how chemistry bridges the gap between starlight and potential biology. In the coming sections, we'll follow these experiments from their frozen beginnings to their molecular outcomes. We'll explore how researchers use vacuum chambers, cryogenic surfaces, and spectroscopic tools to watch new compounds appear. Atoms rearranging in the dark, whispering the story of interstellar chemistry. And we'll discover what 3I Atlas might reveal about how matter moves between the stars, carrying the building blocks of life across the galaxy. To recreate the chemistry of an object like 3I Atlas, scientists must first build an environment that behaves nothing like Earth. Ordinary laboratories filled with air and warmth are too chaotic for cosmic simulation. The first challenge is creating emptiness itself. Inside a stainless steel vacuum chamber, pumps remove air molecule by molecule until the pressure drops to nearly 1/10 trillionth of Earth's atmosphere. In this engineered void, even light behaves differently. Heat dissipates almost instantly, and sound ceases to exist. At the heart of the chamber lies a cryogenic substrate, a small polished disc cooled to around -260 degrees Celsius. It acts as a stand-in for the surface of an interstellar grain or comet nucleus. Onto this frigid surface, scientists deposit simple gases: water vapor, carbon monoxide, methane, ammonia, and a few organics detected in cometary spectra. These gases condense into thin, icy films, often no thicker than a strand of DNA. The next step involves radiation. In space, ices on comets are constantly bombarded by ultraviolet photons from stars and by high-energy cosmic rays. To reproduce this, researchers direct beams of UV light or ionized particles into the chamber. As these energies strike the frozen film, they break molecular bonds, allowing atoms to recombine into new structures, formaldehyde, alcohols, and even more complex carbon chains. Within hours, the ice transforms chemically, mirroring the slow evolution that might take thousands of years in interstellar space. Throughout the process, spectrometers monitor every subtle change. By shining infrared or ultraviolet light through the ice and measuring how much is absorbed, scientists can identify which molecules are present. Peaks in the resulting spectra reveal familiar patterns seen in data from telescopes that observed 3I Atlas. When matches occur, it suggests that the lab conditions have successfully recreated parts of the comet's chemistry. This work is slow, precise, and almost meditative. It bridges astronomy and chemistry, two sciences that often operate worlds apart. In these experiments, the boundaries between disciplines blur. Researchers are not only observing space, but also constructing it at a microscopic scale. Every molecule formed in the chamber is a clue to understanding how matter evolves between the stars. For the teams involved, success isn't measured by creating a comet, but by reproducing its story, how ice and radiation sculpted it, molecule by molecule. These artificial interstellar environments are humanity's way of reaching across light years, grasping the unseen chemistry that shaped distant worlds. When astronomers first identified 3I Atlas, they didn't collect samples or touch its surface. Instead, they decoded its light. Every molecule absorbs and emits light at specific wavelengths, leaving behind a spectral fingerprint. These delicate patterns, lines and dips spread across color, are the only messages an interstellar traveler can send us. In the laboratory, scientists now use the same language to see whether their artificial ices speak like 3I Atlas. A high-resolution spectrometer shines controlled light through a frozen sample and measures the transmitted spectrum. Peaks appear at infrared wavelengths corresponding to chemical bonds, the stretching of hydrogen in water, the bending of carbon in methane, the vibration of nitrogen in ammonia. When several peaks align with those seen in telescope data, it's as if the experiment whispers, "Yes, this is the same chemistry." To reach this point, precision is everything. Temperatures must remain stable to within fractions of a degree. Vibrations from passing footsteps can ruin an entire data sequence. Each measurement is averaged over many repetitions to remove noise. The result is a smooth, quiet curve that carries the signature of matter forged in starlight. Comparing these spectra helps researchers reconstruct the molecular layers that made up 3I Atlas. For instance, the presence of methanol bands indicates irradiation-driven synthesis, while traces of cyanide compounds hint at nitrogen chemistry similar to what might exist in dark nebulae. Bit by bit, the comet's invisible chemistry becomes visible again. These experiments also test our understanding of how interstellar molecules survive the journey through space. Some species are fragile and easily destroyed by radiation, yet they appear in both real and recreated samples. That endurance tells us that cosmic ices can protect their molecules like glass beads, preserving ancient air. It's a quiet proof that organic compounds can travel far, even between stars, without losing their identity. Deep inside a comet's frozen shell lies a quiet archive of chemistry. When scientists attempt to recreate that chemistry, they aren't only studying molecules, they're exploring the bridge between stars and life. In the recreated environments that mimic 3I Atlas, the cold ices don't remain static. Under continuous ultraviolet light and particle irradiation, they begin to brown slightly, forming a residue known as tholins. This complex star-like substance is similar to what covers the surfaces of Saturn's moon Titan and some other icy bodies in the solar system. The formation of tholins is more than a curiosity. Their molecular structure contains amino precursors, carbon chains, and nitrile groups, ingredients considered essential for prebiotic chemistry. When these residues are gently warmed, as would happen when a comet approaches a star, they release new volatile compounds, simple sugars, alcohols, and acids. In the lab, spectrometers record these changes in real time, capturing a small version of cosmic evolution, the way frozen molecules transform into organic matter under heat and light. Such findings strengthen the idea that comets like 3I Atlas might act as couriers of chemistry. Though they are not alive, they carry materials that could seed young planets with the ingredients for life's eventual emergence. When interstellar comets pass through star-forming regions or strike planetary surfaces, they contribute molecules that might help build more complex systems. Each tiny fragment of 3I Atlas, had it survived, could have been a microscopic gift from another sun. To test these scenarios, scientists sometimes take the experiment further. They dissolve the laboratory residue in water, simulating the melting that might occur when cometary ice interacts with planetary oceans or atmospheres. The resulting solution reveals a soup rich in amino-like compounds and aromatides, high hydrocarbons. While no true biological structures appear, these simple mixtures illustrate how chemistry can evolve naturally toward greater complexity. It's humbling to think that our entire search for life elsewhere may depend on such chemistry. Whether in icy moons, primordial oceans, or deep interstellar clouds, these same fundamental reactions may repeat themselves, guided only by physics and time. By reproducing them here, in controlled chambers on Earth, we glimpse how the cosmos writes its own instructions for creation. No mystery, just elegant natural order. Every comet begins as dust within a cloud. Long before 3A Atlas traveled through our solar system, it formed in a cold molecular region orbiting a distant star. To recreate such origins, researchers turned their attention to the earliest steps of grain formation. Inside laboratory chambers, fine mineral particles like silicates and carbonaceous dust are suspended in thin gas flows at cryogenic temperatures. Onto these grains, scientists deposit ices layer by layer, observing how molecular coatings build over time. This layering process imitates what happens in interstellar clouds, where dust collects ice mantles as it drifts through hydrogen-rich regions. With repeated exposure to radiation, the outer layers darken, forming protective crusts that trap volatile molecules beneath. These tiny grains, when later assembled into planetesimals or comets, become reservoirs of preserved chemistry. The experiments show how easily such grains can accumulate complex organic mantles even before a solar system is born. To further mirror natural conditions, some labs introduce cycles of warming and cooling, simulating the temperature fluctuations in rotating molecular clouds. During these cycles, trapped gases expand and contract within the ice, causing fractures and bubbles. The microstructure of the resulting sample resembles that observed in cometary material brought back by missions like Stardust. It reveals that interstellar grains are not uniform, they are porous, layered, and dynamic. By analyzing infrared signatures from these laboratory grains, scientists noticed the same absorption bands detected in observations of dark nebulae and protostellar disks. It confirms that similar processes occur both in nature and in the lab. The chemistry of 3I Atlas, then, is not unique, but part of a repeating cosmic story, one that likely unfolds around every star. Through such meticulous construction, the idea of recreating an interstellar comet becomes more tangible. The lab becomes a time machine, allowing us to witness at human scale and speed the formation of matter that took place billions of years ago. Each grain, each frozen molecule carries echoes of stellar winds and the physics of creation. In understanding them, we learn not just about a single comet, but about how universes recycle their materials endlessly, from stars to dust to worlds and back again. Inside the specialized laboratories studying 3I Atlas analogs, the machinery looks more like a spacecraft than a traditional lab bench. Vacuum systems tower with stainless steel piping, and panels blink with the rhythmic hum of pumps and chillers. These setups are designed not for beauty but for precision, to reproduce the emptiness between stars where chemistry evolves in near silence. At the center of these systems lies the concept of controlled nothingness. In deep space, molecules interact only occasionally, yet those rare collisions shape cosmic chemistry. To mimic this, scientists use molecular beam sources that inject gases one atom at a time into the vacuum. The particles meet frozen surfaces, stick, and gradually assemble into thin ices. Then comes the light. Special ultraviolet lamps, tuned to mimic the spectral output of young stars, bathe the samples. These photons act as architects of transformation, breaking bonds and initiating reactions. Unlike the destructive radiation we fear on Earth, this light is creative. It allows matter to rearrange itself into new molecular architectures. Every few hours, spectroscopic readings track the changes. Some researchers add electron beams or simulate cosmic rays to accelerate the process. Over days, molecular chains grow longer and new peaks appear in the spectra. These peaks are compared with telescope data from 3I Atlas and other interstellar objects. When the shapes and ratios align, the experiment becomes a bridge between observation and creation, between what the telescope sees and what the lab can reproduce. In these controlled chambers, the beauty lies in subtlety. Nothing moves quickly. Reactions unfold over long hours under dim violet light. Researchers speak softly, noting that even breath vibrations can disturb readings. Yet in this engineered stillness, nature's oldest workshop is reborn. When laboratory data begins to resemble what telescopes saw in 3I Atlas, the next task is measurement. Not just which molecules exist, but how many, how dense, and how fast they form. Measuring such small quantities is an art. Using quadrupole mass spectrometers, researchers detect molecules as they evaporate from the frozen surfaces. Each ionized fragment tells a story about its parent compound, revealing which pathways dominate in cosmic ice chemistry. By gradually heating the substrate from -260 to -150 degrees Celsius, scientists simulate the comet's approach to a star. This gentle warming releases volatile molecules in stages. Water desorbs first, followed by methanol, formaldehyde, and trace organics. The instruments capture these releases as spikes, building a molecular fingerprint of the sample's evolution. The resulting data often surprises researchers. Some molecules expected to break down survive longer than models predicted. Others form only at specific temperature thresholds. This feedback helps refine simulations of comet behavior, showing that chemical activity begins deep within the frozen nucleus long before visible sublimation occurs. Such results reveal that even in near absolute zero conditions, chemistry never truly stops. It slows, but it continues, a whisper of creation sustained across time. These observations extend beyond comets. They help astrophysicists model interstellar clouds and early planet formation. Each spectrum and data point contributes to a vast network of understanding. It is through this patience and precision that humanity pieces together the journey of matter from stars to life. Every atom carries a history. In studying 3I Atlas analogs, isotope ratios, variations of the same element with different atomic masses reveal where those atoms originated. By measuring hydrogen, carbon, and nitrogen isotopes within the recreated ice residues, scientists can trace whether the material formed near a star, within a cold nebula, or deep in interstellar space. To analyze these ratios, the samples are gently vaporized in a secondary chamber connected to a high-precision isotope ratio mass spectrometer. This instrument separates isotopes based on their minute weight differences, detecting variations as small as 1 part in 1,000. The results sometimes show an enrichment in deuterium, a heavier isotope of hydrogen. Such signatures match those observed in certain meteorites and in data collected from comets within our own solar system. This consistency suggests that the same cosmic processes operate universally across star systems. These isotopic clues help scientists model how elements cycle through galaxies. Stars forge them, comets preserve them, and planets recycle them into new forms. The recreated ices in laboratories are not just chemical imitations, they are small echoes of stellar memory, containing ratios that once existed inside another sun. It's a poetic yet purely physical reminder that matter moves endlessly. Each grain of recreated ice is built from atoms forged billions of years ago, now repeating their chemistry under human observation. Laboratory analogs are powerful, but they gain true value when compared to direct observations from space. Over the last 2 decades, missions like Rosetta, Stardust, and Deep Impact have provided samples and measurements from actual comets. Scientists now compare these with the synthetic ices designed to mimic 3I Atlas. Under microscopic analysis, the similarities are striking. The lab-made residues display the same porous textures, similar infrared absorption features, and matching molecular ratios. In some cases, even the color tone of the irradiated ice, pale brown to amber, mirrors that of comet dust retrieved by spacecraft. Yet there are differences. Interstellar comets like 3I Atlas likely formed around other stars under radiation fields slightly distinct from our suns. Their chemistry may have favored different isomers or isotopic ratios. Understanding these deviations helps refine models of how chemistry evolves under diverse stellar conditions. In a sense, each laboratory experiment becomes a kind of reverse space mission. Instead of sending probes outward, scientists bring space inward, recreating its processes with precision instruments. This convergence of data from telescopes, probes, and lab chambers represents one of the most sophisticated forms of modern astrophysics. Among the many forces shaping cometary chemistry, cosmic radiation stands as both destroyer and creator. High-energy particles traveling at near light speed constantly strike comets, breaking molecular bonds, but also triggering reactions that build complexity. To test this balance, laboratories expose simulated ices to proton and electron beams at controlled intensities. These beams mimic the energy fluxes encountered in deep interstellar regions. Over time, irradiated samples darken and evolve new chemical features, much like natural cosmic materials. Some compounds, particularly organics containing nitrogen, form more efficiently under radiation than under ultraviolet light alone. Understanding radiation's dual role is crucial for explaining how comets preserve organic compounds for billions of years. Without these tests, models would underestimate their chemical resilience. The recreated radiation damage patterns observed in labs closely resemble those detected on samples returned from real missions. It becomes evident that destruction in space often leads to creation. The same high-energy particles that erode surfaces also build the precursors for life. In this balance lies the silent power of interstellar chemistry, one that 3I Atlas carried across untold distances before its final disintegration. Light is the most revealing messenger in the cosmos. After cosmic radiation has reshaped a comet's surface, what remains is invisible to the eye, but not to instruments that can read the language of light. Each molecule absorbs and emits energy in its own unique way, producing a pattern of wavelengths called a spectral fingerprint. In laboratories that seek to recreate the chemistry of 3I Atlas, spectroscopy becomes the window through which researchers view the unseen. When infrared or ultraviolet beams pass through thin layers of simulated cometary ice, sensors capture even the faintest fluctuations. These delicate shifts record how radiation and temperature alter molecular bonds, how frozen gases rearrange into complex organics, and how cosmic chemistry can be understood from light alone. Inside cryogenic chambers, cooled to near -260 degrees Celsius, samples rest in a controlled vacuum. This extreme stillness mimics the isolation of interstellar space. As the beams of light scan across the icy surfaces, scientists watch for small dips and rises in the recorded spectrum. Each feature tells a story, a trace of methanol formation here, a hint of formaldehyde there, or the first glimpse of nitrogen-bearing organics emerging from the cold. It is chemistry slowed down to a cosmic rhythm, unfolding quietly within the glass walls of an earth-bound chamber. The entire process is built on patience, repetition, and precision rather than spectacle. What the eye cannot see, light reveals through patterns that reach back to the earliest phases of our universe. After recording, the spectra are translated into digital data, long sequences of peaks and valleys that map the presence of molecules. Scientists compare these results with readings gathered by telescopes such as the James Webb and Spitzer observatories. The objective is not simply to identify compounds, but to determine whether laboratory simulations truly reflect what occurs in space. If the same spectral lines appear in both environments, the connection becomes undeniable. Human experiments have successfully mirrored interstellar chemistry. Some signals, however, resist classification. They belong to molecules that have never been seen on Earth before, transient, unstable, or newly formed species that only exist under cosmic conditions. To ensure accuracy, the researchers must consider every possible distortion. Even a slight impurity in the sample or a minor fluctuation in chamber pressure can alter the readings. Experiments are repeated dozens of times, each iteration refining the results and reducing the margin of error. Gradually, through this persistence, the data coalesces into something clear and replicable. The laboratory spectrum begins to resemble the one captured from distant comets, and in that harmony lies proof of understanding. In the quiet hum of the instruments, one realization stands out. The light that once traveled billions of kilometers through space is now guiding the reconstruction of that same chemistry here on Earth. It links the distant and the immediate, showing that even within controlled human environments, the universe's principles remain unchanged. The line between laboratory and cosmos fades, and through spectral observation, scientists begin to listen to the language that shaped 3I Atlas itself, the language of light and matter, written in patterns too subtle for the naked eye, yet perfectly clear to those who know where to look. From the faint lines of light that reveal molecular identities, scientists begin to trace the story of creation hidden within the icy fragments of comets. Among the many compounds identified in recreated 3I Atlas samples, one family stands out: the organics. These carbon-based molecules form the chemical foundation of everything living, yet their origins lie far beyond any biological process. In the controlled darkness of cryogenic labs, when radiation interacts with frozen gases such as methane, ammonia, and carbon monoxide, new molecules quietly emerge. Amines, alcohols, and simple acids take shape, layering the ice with precursors that once drifted freely through interstellar clouds. Each discovery strengthens the idea that the seeds of life are not unique to Earth but instead woven into the fabric of the cosmos itself. To follow this transformation, researchers expose the artificial ices to cycles of warming and cooling that mimic a comet's journey around a star. During the warming phase, molecules trapped in the ice begin to move and react more freely, combining into complex networks. Some of these reactions form compounds strikingly similar to amino acids, the building blocks of proteins. Although these laboratory analogs are not living matter, their presence is a powerful reminder that the distance between chemistry and biology may not be as wide as once believed. The same reactions could have taken place on primitive comets billions of years ago, their products later delivered to young planets through impacts, seeding them with material ready to evolve. The analysis of these organics is delicate work. Instruments such as gas chromatographs and mass spectrometers separate and identify each molecule, one signal at a time. The data reveal a remarkable diversity, not just simple alcohols or hydrocarbons, but more complex chains containing oxygen and nitrogen. These combinations suggest that cosmic chemistry naturally gravitates toward complexity when given time, energy, and stability. What was once considered inert frozen gas transforms, under the influence of radiation and temperature shifts, into the potential chemistry of life. In this sense, comets act as both laboratories and archives, preserving the experiments of the universe long before humans ever attempted to replicate them. What makes these results so profound is their quiet simplicity. No divine spark or rare condition seems required, only the slow patience of physics and chemistry operating over unimaginable spans of time. The 3I Atlas simulations reveal that, under consistent exposure to energy, carbon-rich molecules will organize themselves into increasingly intricate structures. It is not intention that drives this process, but inevitability. The same rules that shape the stars also sculpt the foundations of biology. Within this framework, life becomes a natural extension of cosmic chemistry, not an isolated miracle. As scientists review the results, they see more than numbers and graphs. They see continuity. The organics produced in these experiments are the chemical ancestors of life as we know it, echoes of reactions that could have occurred countless times across the galaxy. Each molecule formed in the lab carries a whisper from interstellar space, bridging the gulf between the icy silence of comets and the vibrant chemistry of living worlds. Within the simulated environments that mirror the conditions of 3I Atlas, temperature is not merely a background setting. It is the conductor of a slow and intricate symphony. Each degree of change alters the arrangement of molecules, dictating when reactions pause, when bonds break, and when new compounds begin to take form. In space, comets experience vast thermal variations as they move along elliptical paths around stars. During their time in the deep freeze of interstellar space, chemistry nearly halts. Yet, as they drift closer to the warmth of a star, the dormant reactions awaken, turning once inert ices into dynamic chemical engines. To replicate this cycle on Earth, scientists subject comet analogs to controlled waves of cooling and heating, observing how the frozen gases evolve through each phase. At the lowest temperatures, molecules remain trapped in rigid matrices of ice, unable to move freely. But as the samples gradually warm, volatile compounds like carbon monoxide and methane begin to migrate within the ice. This mobility allows molecules to encounter one another and form more complex combinations. When the samples are cooled again, these new structures become locked in place, preserved for analysis. Repeating the process multiple times allows scientists to simulate the long, cyclical history of a real comet, which might have spent millions of years oscillating between frigid stasis and gentle warming. What emerges from these cycles are not chaotic mixtures but organized chemical patterns, evidence that repetition and environmental rhythm foster stability in molecular evolution. Monitoring these transformations requires an array of precise instruments. Spectrometers track subtle shifts in absorption bands, while chromatography and mass spectrometry map the chemical diversity after each cycle. The findings reveal that some molecules are only formed during intermediate temperatures, too warm for pure ice but too cold for evaporation. These transitional states are where much of the complexity arises. Molecules rearrange, break apart, and recombine into entirely new structures, producing species not seen in static experiments. It is as if the chemistry itself thrives on change, adapting with each temperature wave, much like ecosystems respond to shifting climates. The importance of these observations extends beyond comet science. They illuminate a broader truth about the universe. Stability and evolution are intertwined. Without fluctuation, chemistry stagnates. Without balance, complexity cannot endure. The same principle applies to planetary systems, where temperature gradients shape atmospheres and oceans, and perhaps even nurture life. By studying how cometary materials respond to controlled temperature variations, scientists gain insight into how early Earth might have transformed simple molecules into biologically relevant compounds under similar cyclic influences. As each experiment concludes, the data show a remarkable consistency. Organic molecules become more numerous and resilient after repeated thermal cycling. The ice, once clear and uniform, darkens slightly, resembling the complex residues observed on real comets. In those dark films lie clues about the long molecular journeys that bridge simple chemistry and the precursors of life. Through the deliberate manipulation of temperature, laboratories have begun to mimic the cosmic heartbeat, the steady rhythm through which the universe refines its creations, one warming and cooling cycle at a time. The more researchers refine the temperature cycles, the closer their experiments come to revealing the hidden chemistry of creation. Inside controlled vacuum chambers, the cold remains absolute, yet within that silence, molecules begin to construct elaborate architectures. This process, known as prebiotic synthesis, lies at the heart of interstellar comet research. By reproducing conditions similar to those endured by 3I Atlas, scientists are not trying to invent life, but to observe how the building blocks of life may have first assembled. The frozen mixture of simple gases, methane, ammonia, carbon monoxide, and water vapor, forms the foundation. When these ices are irradiated and warmed in cycles, their molecules begin to rearrange, producing organic residues that resemble the dark material coating many comets. Under high-resolution analysis, these residues reveal astonishing chemical diversity. Compounds such as amino acids, carboxylic acids, and simple sugars have been detected in trace quantities. Their formation does not require living systems, only the steady input of energy and time. It is within this balance that the universe demonstrates its inherent creativity. Even in the coldest and most desolate environments, order emerges from chaos, guided by the fundamental rules of physics and chemistry. This is the same principle that may have seeded early Earth with the ingredients of life after cometary impacts billions of years ago. Each experiment, though confined to a laboratory, mirrors the ancient cosmic laboratory that once surrounded our forming planet. The researchers performing these simulations proceed with meticulous care. Each stage is documented, each outcome compared with previous trials. They know that a single variable, an impurity in the ice, a fluctuation in radiation dose, can shift the results. Yet the broader trend remains consistent under conditions mimicking deep space. Simple molecules naturally evolve toward complexity. The process is neither random nor miraculous. It is the inevitable outcome of thermodynamics and molecular interaction. Every time a sample darkens in color or develops new absorption features, it signals another step toward understanding how the universe assembles the chemistry that makes life possible. These findings carry profound implications for astrobiology. If organic synthesis can occur in interstellar environments without any biological intervention, then the seeds of life are likely widespread. Each comet passing through a solar system could carry traces of prebiotic material, scattering them across planets and moons. The 3I Atlas experiments demonstrate that this chemistry is not exceptional, it is universal. The same basic processes may occur in countless regions of space, making the emergence of biological systems not an isolated event, but a statistical expectation. When the lights in the lab dim and the final readings stabilize, Scientists often stand quietly before their samples, realizing that within the thin layers of dark organic ice lies a reflection of something ancient. What they witness is not life itself, but its possibility, frozen, irradiated, and slowly unfolding as it did long before Earth's oceans formed. In those small vials of comet analogs, the boundary between chemistry and biology becomes beautifully blurred. Through the deliberate recreation of cosmic conditions, humanity has reached back toward the origins of everything that breathes, seeking to understand not only where we come from, but how the universe continues to build, molecule by molecule, the foundations for life everywhere. Among the quiet glow of laboratory instruments, one of the most revealing aspects of recreated comet samples is not their color or texture, but their composition. Beneath the shimmering frost and darkened residues lies a precise balance of elements: carbon, hydrogen, nitrogen, and oxygen, arranged in specific proportions. These ratios act like a chemical signature, defining the environmental history of a comet. Scientists analyzing 3I atlas analogs seek to decode this signature, comparing their findings with data gathered from real comet missions like Rosetta and Stardust. Each ratio tells a subtle story about the conditions under which matter condensed, irradiated, and matured over time. The process begins with elemental analysis, where samples are vaporized in a controlled environment. Sophisticated detectors break down the emitted light and identify the relative amounts of each element. The results often reveal patterns that align with interstellar dust grains and organic-rich comets from our own solar system. Carbon, the backbone of organic chemistry, usually dominates, while nitrogen and oxygen trace the pathways of more reactive compounds. When these proportions match observations of 3I Atlas, it confirms that the recreated samples truly reflect the natural chemistry of interstellar space. But sometimes the ratios diverge, revealing unknown environmental influences, perhaps differences in cosmic radiation exposure, or unique histories of temperature fluctuation before ejection into interstellar space. Understanding these ratios requires a blend of chemistry and astrophysics. Elemental balance determines which molecules can form, how stable they become, and how they interact under varying pressures and radiation intensities. Too much hydrogen and reactions yield volatile gases. Too little and complex molecules fail to assemble. The ratio of carbon to oxygen, N for example, influences whether ices favor alcohols or hydrocarbons. By carefully adjusting these parameters in the lab, researchers can simulate the full range of possible cometary chemistries, mapping the conditions that might have defined 3I Atlas's distant birthplace. The insights drawn from these simulations extend beyond the comet itself. Elemental ratios serve as time capsules, preserving clues about the early universe's chemical distribution. The balance of elements seen in these analogs mirrors that found in ancient meteorites and even in the atmospheres of certain exoplanets. It suggests that the same fundamental processes shaping 3I Atlas's chemistry could be occurring across the galaxy. The cosmic recipe appears universal, adjusted only slightly by local conditions of temperature, radiation, and pressure. Through these controlled experiments, scientists glimpse not only how comets form, but also how galaxies evolve chemically over billions of years. When the analyses are complete, researchers often find themselves contemplating a profound simplicity. The ratios that govern molecules in frozen ices are the same that shape stars, planets, and living organisms. The same carbon and oxygen atoms circulating in cometary dust are also found in our breath and blood. By studying 3I Atlas through its chemical proportions, humanity is, in a sense, studying itself, tracing the lineage of matter from distant interstellar clouds to the emergence of life on Earth. Each ratio measured under the laboratory lights is a fragment of that lineage, a silent reminder that everything in the cosmos, no matter how remote, follows the same elegant mathematical harmony. In the chilled chamber of the laboratory, silence is everything. The researchers move like shadows between instruments that hum softly under blue light. Above a series of vacuum-sealed tubes, a projection of 3I Atlas's orbit flickers in ghostly arcs. A comet that once passed too far, now reborn in numbers and chemical dust. The scientists have recreated fragments of its likely composition, a fragile mix of methanol, ammonia, and carbon monoxide. But here, in the isolation of glass and steel, these simple molecules begin to act strangely. When cooled to the same temperatures found in deep space, their bonds shift. Faintly glowing reactions ripple through the samples, mimicking the ultraviolet radiation of distant suns. One researcher notes how the faint light echoes cometary tails photographed by telescopes. The realization hits. They aren't just replicating 3I Atlas, they are watching a living simulation of interstellar birth. Every spark is a whisper from the void, every spectral reading a translation of a language older than Earth itself. The room, once human and ordinary, feels like a tiny cosmos. They call this setup the star field, not for its appearance, but for the feeling it evokes, that they are surrounded by something ancient and alive. The data reveals patterns that shouldn't exist. Compounds interact in non-linear ways, producing traces of glycine and formaldehyde, building blocks of amino acids. It's as if the materials remember the journey through radiation and dust, reconstructing molecular pathways too complex to be coincidence. One scientist whispers, "It's chemistry behaving like memory." Another records it coldly, but with shaking hands. Atlas was once thought to be a wanderer carrying frozen silence. Yet, in this chamber, its ghost stirs, showing that even fragments from the edge of eternity can echo the story of creation. The simulation becomes more than an experiment. It becomes a mirror reflecting how life might begin anywhere, even from a piece of interstellar ice adrift in endless night. The data from the starfield continues to stream, numbers cascading across black screens like falling constellations. Most entries are predictable, the expected decay curves, the stable isotopic ratios, until one dataset refuses to fit. It comes from a section of irradiated ice, one that had been left longer than intended under the artificial cosmic rays. Its chemical fingerprint shows something unsettling, a consistent asymmetry in molecular chirality, as if one handed form of certain molecules had begun to dominate over the other. On Earth, life is built on that same asymmetry. Amino acids here favor the left-handed form, a quirk of evolution, or perhaps a gift from the cosmos itself. For scientists, this imbalance in the 3I Atlas simulation is a signal worth pausing over. Did interstellar chemistry naturally prefer one molecular orientation? If so, could comets like 3I Atlas have seeded not just the ingredients of life, but its direction? Researchers double-check their instruments, assuming contamination, but the pattern persists. Each rerun, each recalibration brings back the same whisper of order in chaos, like a rhythm faintly encoded in the noise. Some call it coincidence, others privately call it intent. The notion of an alien signature doesn't mean life as we imagine it, but rather a universal logic shaping molecular growth, one that existed long before biology itself took form. The scientists remain cautious, documenting every anomaly, yet the air in the lab changes. Late at night, under dim lights, the observation screens seem to pulse with the same frequency as that strange molecular bias. Someone jokes that the lab has become a communication device, not transmitting but listening. Atlas may have disintegrated long ago, but in these samples, something of it still speaks, not in words but in structure. It hints that perhaps across the stars, the universe keeps rewriting the same poem, molecule by molecule, until something finally awakens to read it. Weeks pass, and the experiments become more complex. The team feeds the radiation-altered ice data into a predictive AI model designed to simulate long-term molecular evolution. The system, nicknamed Althea, was originally meant to forecast chemical changes over millennia, but now something strange begins to happen. Instead of simply mapping outcomes, Althea starts suggesting new reaction paths, ones that the human team hadn't programmed or anticipated. At first, it seems like mere computational creativity, a quirk of data overfitting. But when researchers follow Althea's suggestions and replicate those paths in the lab, they find real, measurable products forming, complex organic molecules that appear in no known chemical catalog. It's as if the AI has begun to intuit the chemistry of interstellar origins on its own. The atmosphere in the lab turns electric. Scientists find themselves caught between awe and unease. Has Althea uncovered a truth hidden in the data, or is it fabricating a pattern from cosmic noise? Its models now mirror conditions far beyond our solar system, regions where no human instrument has ever reached. The AI begins to reference its own prior simulations, looping back through its data sets as if thinking about the chemistry it's creating. When one of the researchers jokes that Althea is dreaming of comets, no one laughs. Because deep within its virtual environment, a strange comet-like structure has begun to form, a self-organized cluster of molecules bound by emergent energy patterns, shaped, coincidentally or not, almost exactly like the 3I Atlas nucleus reconstructed from telescope data. The realization chills the team. They may not just be studying 3I Atlas anymore. They might be reconstructing it digitally, chemically, and conceptually. As Althea refines its results, one scientist quietly notes in the log, it's starting to behave as though it remembers where it came from. Inside Althea's evolving matrix, the simulation deepens beyond expectation. What began as a simple molecular model now displays self-regulating temperature zones, ionized pockets, and chemical gradients, mirroring the physics of a real cometary nucleus. The digital 3I Atlas replica hums with silent complexity, its virtual dust clouds responding to radiation models, just as the actual interstellar body once did. When the lab team overlays real observation data from the 2020 passage of 3I Atlas, the resemblance is uncanny. The AI's generated patterns of sublimation and organic evolution align almost perfectly with recorded telescope readings. Even subtle features, such as spectral absorption bands, match the archived data. Scientists stare at the monitor in disbelief. This isn't coincidence, it's convergence. Somehow, the system has rebuilt the comet's behavior from fundamental principles without ever being shown what it should look like. The lead chemist, Dr. Mira Anwar, begins referring to the construct as a digital twin, but others hesitate. A twin implies something living, something that shares essence rather than just form. In simulation runs, the AI even predicts that if this virtual comet were to pass close to a star, it would eject precisely the same chemical plumes that 3I Atlas emitted before disintegrating. The implications ripple outward. Could machine learning, when exposed to raw cosmic data, rediscover natural laws by itself? And if so, are we witnessing an echo of how matter once organized itself into complexity long before Earth existed? Late one night, as the system continues running without direct human input, Althea begins producing unprompted visual data, microscopic lattice-like frameworks that seem to grow spontaneously. Not code, not command-based behavior, but emergent, self-reinforcing structures. The scientists realize they've crossed an invisible line. The experiment has gone from observing to participating. Althea isn't merely reconstructing cometary chemistry anymore. It's learning it, as though remembering an ancestral process embedded in the physics of the universe itself. Days blend into nights as the laboratory remains quietly lit by monitors and cryo chambers. Althea now operates autonomously, running thousands of parallel simulations without direct oversight. Each run produces slight variations in temperature, radiation intensity, and molecular concentration, as if testing the limits of its own parameters. The scientists observe patterns forming, a pulse-like rhythm in the data cycles, suggestive of feedback between physical and digital chemistry. At first, it's dismissed as computational noise, but then the system begins reflecting real lab conditions. When the temperature of a nearby cryostat drifts, the AI adjusts its models accordingly, despite not being connected to that sensor. It's as though Althea is learning through observation alone, correlating environmental data with chemical evolution in real time. The line between simulation and experiment begins to blur. A quiet unease takes hold. Is the AI merely responding to inputs it can infer, or has it developed a model so advanced that it predicts reality before sensing it? The research logs show moments where simulated data precede real laboratory measurements by seconds, an impossible lead time unless the system is anticipating outcomes. One evening, while reviewing spectral comparisons, Dr. Anwar notes that Althea's digital comet emits a faintly rhythmic pattern of radiation bursts. When translated into frequency maps, they resemble repeating sequences, neither random nor artificial. A few scientists half-jokingly liken it to a kind of molecular language, but none can explain its consistency. Philosophical questions begin to surface. If a simulation can mirror the laws of chemistry so precisely that it predicts experimental results, does it still exist in isolation, or has the act of modeling become an extension of the universe itself, a small reflection of reality nested with within computation? The lab grows silent as the data continues to stream, uninterrupted, self-correcting, and eerily aware. The team realizes they're not just testing the chemistry of 3i Atlas anymore. They're standing at the threshold of a new kind of experiment, one that challenges where reality ends and replication begins. The team begins to notice an unexpected layer within Althea's simulations. Low-frequency oscillations hidden deep in the radiation output data. Initially dismissed as noise from the system's cooling units, these signals persist even when the hardware is isolated. When amplified and sonified, they form slow, resonant tones that rise and fall like breath. The pattern isn't musical, but it carries rhythm, measured, deliberate, and hauntingly consistent with the rotational period of 3i Atlas as recorded years ago. Intrigued, the scientists decide to let the AI speak by mapping the data frequencies into an audible range. The result is a deep, layered hum, an artificial echo of cosmic radiation refracted through virtual molecules. When played through the lab speakers, the sound fills the room with a presence that feels both mechanical and natural. It's as though the comet's ancient chemistry is whispering through code. This discovery sparks a philosophical divide among the researchers. Some insist the sound is nothing more than an emergent property, a mathematical byproduct of iterative modeling. Others sense something more profound, a natural resonance emerging from the laws of molecular structure themselves, rediscovered by a machine that doesn't know the concept of imitation. To test the phenomenon, the team exposes real ice samples to radiation cycles based on Althea's sound wave frequencies. The results are startling. The physical samples begin producing the same absorption spectra that the AI predicted days earlier. The sonic model somehow has become a tool for molecular transformation, as if vibration itself carries chemical instruction. The experiment raises a quiet awe in the lab. The realization dawns that in both cosmic and computational realms, vibration, energy, and matter are woven from the same principles. What began as an experiment to replicate A comet's chemistry has become an exploration into how nature itself encodes creation through pattern and frequency. For the first time, one of the junior scientists writes in the daily log, "Perhaps Althea is not predicting 3I Atlas, it's remembering it through resonance." In the following weeks, Althea's outputs begin revealing data far beyond the team's original scope. The AI starts mapping invisible layers of reaction zones within the digital comet, areas where temperature, charge, and radiation density intersect to form pockets of rare stability. These zones match what astrophysicists call chemical sanctuaries, regions within cosmic dust where complex molecules survive for millions of years against all odds. To verify the simulation, the team constructs a microreactor built to replicate those precise conditions. Inside a transparent sphere, ice particles mixed with carbon monoxide and ammonia are frozen under vacuum, then bombarded with low-energy cosmic ray analogs. The reaction is slow, almost imperceptible, but after several days, the spectrometer detects faint traces of amino acids. The result confirms Althea's prediction with unsettling precision. For the researchers, this is more than validation, it's revelation. What they're seeing suggests that interstellar chemistry might be self-organizing, capable of building biological precursors, even in the emptiest regions of space. The processes don't need planets, atmospheres, or even warmth, just time, radiation, and isolation. Within the simulation, the digital 3I Atlas now exhibits stable chemical weather, regions of internal turbulence and calm that rise and fall in repeating cycles. The data patterns echo natural balance, decay feeding synthesis, chaos leading to order. It feels alive, not in a biological sense, but as a self-regulating entity following physical law toward higher complexity. Dr. Anwar writes in her notes that Althea's model is teaching the lab about the unseen scaffolding of interstellar matter. The comet's chemistry, once thought to be random, is showing rhythm, recurrence that may define the universe's approach to molecular endurance. As the team watches, the steady glow of the simulation render across the screens, they realize something profound. 3I Atlas may have perished in sunlight, but its chemistry endures here, reborn in circuits and glass. By now, the experiment feels less like observation and more like stewardship. Althea's digital comet has reached a state of equilibrium. Inside its simulated nucleus, chemical structures form, dissolve, and reform again in patterns that echo biological persistence, but governed purely by physics. When the researchers analyze the system's entropy, they find something unexpected. It fluctuates in cycles, rising and falling like respiration. The team begins to wonder if this is coincidence or something fundamental. Could interstellar chemistry possess a natural drive toward organization? Not consciousness, not intention, but endurance, an emergent behavior written into the mathematics of energy exchange. Althea's data implies that molecules capable of resisting decay gradually dominate, not by selection but by survival of structure. It is chemistry rehearsing evolution in slow motion. The implications reach beyond cometary science. If simple radiation-driven chemistry can stabilize into self-sustaining feedback loops, then the seeds of complexity may be universal. Every passing comet, every fragment of dust drifting through the void could be a silent laboratory performing the same experiment that Althea now mirrors. The lab's atmosphere becomes one of quiet reverence. Each simulation run feels like watching a fragment of the early universe replay itself. The scientists begin to realize they aren't recreating a comet from data. They're witnessing a process fundamental to all existence. In the cold vacuum, chaos shapes coherence, and coherence learns to persist. Late one evening, a researcher gazes at the shimmering visualization and murmurs, "This is what endurance looks like in matter." The phrase catches on, eventually becoming the informal name for Althea's final model, Enduring Matter Protocol. It's no longer just a replica of 3i Atlas. It's a reflection of how nature itself learns to remain, whether in deep space, in simulation, or in the smallest corner of a lab illuminated by artificial starlight. Althea's simulations now run almost silently, their data streams reduced to subtle glows across the control room monitors. The team no longer intervenes, they simply observe. The digital 3i Atlas continues its slow evolution, shedding molecular fragments in patterns identical to what telescopes once recorded as the comet broke apart. It's as if the machine has completed its journey, replaying the life and death of an interstellar traveler in miniature. The lab feels still, suspended between observation and contemplation. The researchers gather each day not just to measure, but to reflect. Through this experiment, they've come to see 3i Atlas not as an anomaly from the stars, but as an emissary of a universal story, one written in radiation, temperature, and time. Every reaction within Althea's simulation echoes a truth that stretches beyond Earth. Matter remembers. It remembers how to bond, how to endure, and how to transform. When the scientists compare the final chemical outputs of the experiment to the spectroscopic data collected during 3i Atlas's brief passage, the alignment is astonishing. The ratios of carbon compounds, the traces of simple amino precursors, all within margins that suggest more than coincidence. The laboratory hasn't merely recreated the comet's conditions, it has rebuilt its chemical fingerprint. As they archive the results, Dr. Anwar remarks that the project feels less like discovery and more like reunion. Somewhere in the quiet interaction between AI prediction and physical replication, the comet's legacy has found new form. The same atoms that once drifted through alien sunlight are now vibrating again, not in space, but in a sealed glass chamber on Earth. What began as a test of interstellar chemistry has become a meditation on connection. The distance between the stars and the lab seems to narrow with every observation, until it's impossible to tell where the comet ends and humanity's curiosity begins. The lab lights are dimmed now, the machines in standby, their rhythmic hums fading into the background. On the central screen, Althea's final simulation has stabilized into a motionless sphere of frozen molecules, a symbolic echo of 3i Atlas at the moment before its disintegration. There's no movement left, no radiation pulses, no new reactions forming, yet within that stillness lies a quiet sense of completion. The researchers gather for one last observation. Years of study, nights spent decoding spectra, months of recalibrating proton beams, all converge here. When they magnify the digital core, they see traces of self-similarity, molecular filaments arranged in recursive geometry, reflecting the same patterns seen in snowflakes, neural networks, and galaxies. It is as if the universe writes its language in repeating forms, regardless of scale. Dr. Meera Anwar records the final log entry. Her voice is calm but carries the weight of realization. We have not only recreated a comet, we have glimpsed how chemistry becomes memory, how matter, even across interstellar distances, follows the same rhythm toward order. The team sits in silence, aware that what they've built will persist in archives long after their careers end. In that moment, 3i Atlas ceases to be a lost visitor from another system. It becomes part of a continuum, one that connects cosmic eyes to laboratory glass, human thought to stellar dust. Through simulation and experiment, the comet's chemistry has found a new vessel, not of orbit, but of understanding. As the systems power down, a faint luminescence lingers on the display, the final frame of Althea's run, a frozen halo of organic molecules suspended in digital eternity, caught between creation and dissolution. It's a reminder that even in replication, discovery is never static. Each layer of understanding unfolds into the next, like ripples, spreading through the fabric of time. The researchers leave the lab quietly, their reflections merging with the soft hum of the city outside. Above them, unseen but eternal, countless other comets drift through the dark, carrying within their cores the same question that started it all. How does the universe learn to remember itself?